Okay. Yeah. So today we're going to be. That's okay. I think that's better. Okay. Yeah. So today we're going to be continuing with flight operations, and then after that we'll be doing cross-country planning, and then some other stuff. I think whatever Eli has for us. So we'll start by reviewing runway numbering. So the numbers on runways, I mean, you've probably seen this all the time, and then wonder what they meant. It's the magnetic heading of the runway, the nearest 10 degrees. And there's some exceptions to that in like Alaska and Canada, where runway headings or where magnetic headings vary quite a lot. And then so now we're going to talk about the segment and circle. The written test has some questions about this. It's kind of a weird little thing. So first, I think we have to go over traffic patterns. So how can I use the whiteboard?
Guys, just a pointer. I think there's an echo on Zoom. Can you mute one yourself?
Probably have both muted.
Yeah, I muted yours. We're good.
So I think that one.
How can I raise one of the screens? Okay. So, what about traffic patterns? If I can turn that projector on. Anyway, it doesn't really matter. Essentially, either of them. So this is our sample runway. The way that we land in general on runways is we fly something called a traffic pattern. So I'll assume that we're landing on runway 27, which means that we're going to be landing to the west. So the way we do this is called our wind. For context, we always land into the wind. So the wind is going this way, and winds are always from. So if you hear wind, the winds are from that direction. So in this scenario, we have a wind from 270. So the way we land is we fly this first flight called. This is called the downwind because you're flying with the wind, right? And then you turn. Most of the time, traffic patterns are to the left, like meaning that you make left turns. So here we have a left downwind, and we just kind of maneuver the plane along this way, and then we fly our downwind out, and then we turn left, and then this is called our base site. So this is this. Downwind. And then generally you turn base, if you turn your base like at 45 degrees, this should be a 45-degree angle from the end of the runway. So that's called relative bearing. Really super applicable right now. And then once you are lined up with the runway, you turn. Does that make any sense? Yeah, so then you land and then you have this leg, which is called your upwind. And generally, the part this way, or this way. And then if you're staying in the pattern, then you can turn right. You're locked in this space, and that's called crosswind. And then you turn right to your time. So the way we enter a traffic pattern in general is 45 degrees to the downwind. It doesn't have to be exactly 45 degrees, but you'd be flying in 45 degree entry and then turn to parallel the runway. So that would be a heading of 90 degrees. And then so this would be the heading of 45. You want this up. This is just kind of a prerequisite for what we're going to talk about next. But does anybody have any questions about traffic patterns? So now we have this thing called a segmented circle. And a segmented circle is to kind of designate how traffic patterns are flown for a particular runway. So you can think of these markings right here as this is your base leg, and then this is your final. So this indicates a right base for this would be runway 18 because it's going to the south. Does that make sense? And then this would be a right base, or yeah, a right base to final for runway 27, and then this would be a left base for runway 9, and then this would be left traffic for runway 36. So and then you also have a windsock. So this wind is saying that the wind is coming, or the windsock is saying that the wind is coming from this direction, right? So the proper runway to land on would be this runway because you want to land into the wind. So yeah, it shows the base to final turn, and then yeah.
Where's the 36 in the fleet?
We kind of have to imagine that. So this would be runway 18, right? Like this one, if you're flying, so north is up, right?
Right.
So then this is for runway 18 because you're landing to the south. Does that make sense?
Wow.
And then this would be runway 36.
Why is it 18?
Because it's magnetic, the magnetic heading is due south. So south. Yeah. Oh, so did we even cover that? How everything okay.
I don't know where we would have covered it. I don't know.
Okay, gross oversight on my part. So the way that we measure, like, that we navigate with airplanes is in degrees, right? So we have our compass rounds right here, and north. So north is 360, and then east is 90 degrees, and then south. West 270. So if you have a runway like this, let's say our runways on our compass rose, this runway is going to be 36, and then this is going to be 18 because you're landing to the south, the top one, and then on this bottom one you're landing to the. So does that answer your question?
Yeah, thank you.
And then generally that's how we navigate pretty much everywhere in aviation. Like you'll have a compass or a directional gyro, and it's it'll indicate your magnetic heading in degrees, right? So yeah.
So how do you decide here between
Where would we see this L shapes?
So the L shape would just be on an airport. You would just see it. See if I can. Yeah, it represents the traffic pattern. I'm sorry for being kind of like, yeah, so this is just on, okay, that's kind of a bad picture. But that you would just see it on top of an airport. Like when you overfly the airport, it would just be on the ground. Do you see that? So then here's a better picture. The L shape represents the base to final turn. Does that make sense? So for runway, this picture is extremely shitty because it's not north up. So realistically, north would be to the left, if that makes any sense, which is so unconventional. But yeah, so let's see if I can find a better picture. But, yeah, Eli, do you have anything to add? Should segment in circles?
So it sort of tells you what the traffic pattern.
Yeah, it does exactly tell you the traffic pattern. So this says left traffic for 3-6, right? Because this is your base, and then that's your final leg.
Required to follow that.
Like at a controlled airport, there is not really a set traffic pattern when the control tower is in operation, because they control how things are operated. So like the tower might tell you like make a right base for runway 12 right or something, or they could say right base for 12 left, but that would be really unconventional because you don't land that way on parallel runways. But yeah, but at a controlled airport, you're not required to follow it because it doesn't really apply. But then at an uncontrolled airport, it's not technically regulatory, but it's strongly recommended because a lot of airplanes or not a lot, but technically speaking, some airplanes at non-controlled airports could not have a radio. So you could get into a mid-air collision if you're flying conflicting traffic patterns. So yeah, so any more questions about the segmented circle? Okay, yeah, so here's a diagram. This is how we fly traffic patterns. So 45 entry to the downwind, and then the downwind is with the wind, and then you make a base turn, and then final, and then yeah, and then you have upwind, crosswind, and then I think they say 45, like the recommended departure is either straight out or 45 degrees in the direction of your turns. Yeah, so a written test question based on an image like this would say, what's the preferred runway to land on? And what would be the correct traffic for that? So technically there are 2 correct runways that you could land on given this wind, right? So it makes sense that the wind is coming from the opposite direction that the windsock is pointing, right? Because the wind is filling the windsock. So the correct runways to land on would either be runway 27 here or runway 36. And the written test question would be like right traffic for 36 or left traffic for 36, and the correct answer would be left traffic because it's left turns. But yeah, and then we have this thing called LASSO, or land and hold short operations. And the FAA wants you to know about this. Student pilots should not participate in LASSO. The pilot in command always has the authority to accept a LASSO clearance. Pilots should deny a LASSO clearance if they are unfamiliar. And then distance info is available in the chart supplement. You need 3 statute miles of visibility to be able to accept a LASSO clearance, and then runway hold position sign denotes intersecting runways. So I'll kind of explain this more in detail. So a LASSO clearance would be like you're cleared to land, and then they say hold short at an intersection. So they're not letting you use the full runway distance. And that's why the FAA emphasizes that if you don't feel comfortable accepting a LASSO clearance, that you shouldn't accept it. So that's basically where you land, and then you're told to hold short at a specific point. So yeah, if you're unfamiliar with LASSO, don't use it. Okay, so
Holding short just means stop before you get
to a specific point. Like there would be, I'll pull up another. Yeah, so holding short would, the FAA would say, or I guess the clearance would be cleared to land runway 27, hold short of like this point, which they might call like taxiway Bravo. So they would say like you're cleared to land on 27, and then you have to hold short of this point. So yeah, I mean, just don't accept a lasso clearance in general. I mean, most airports don't even do lasso, but yeah. So now we're going to talk about taxiing in strong winds. So in general, if the wind is coming from the in front and to the left of you, use aileron, up aileron on the left-hand wing and neutral elevator. So up aileron would mean that you turn the yoke to the left, and then neutral elevator. And then the opposite of that, if the wind is coming from the right of you and in front of you and to the right, so up aileron, and then neutral elevator, so that would be the yoke to the right, and then like in the middle, or no yoke pressure. And then if it's coming from behind you, it says down aileron on left hand wing, and then down elevator, so that would mean push the yoke forward, and then put it to the right, so the elevator. Yeah, this is just taxiing in a wind. So if you're taxiing on the surface and then there's a really strong wind, then that's just how they want you to use it. Yeah, and then opposite of that. So, and then we also have this thing called aeronautical decision making. So the FAA puts strong emphasis on making good decisions when you're flying airplanes. So they have these things called hazardous attitudes. It's kind of odd. So, and each one has a corresponding antidote. So there's 5 of them, and you can remember them with the acronym, or I guess it's an initialism, AIMR, AIIMR. So anti-authority, invulnerability, impulsivity, macho, and resignation. So anti-authority is, I mean, they're all just exactly what they sound like. So the antidote to anti-authority is follow the rules. And then the antidote to invulnerability is it could happen to me. And then with impulsivity, it's not so fast, think first. And then macho is taking chances is foolish. And then resignation is I am not helpless. So, I mean, this is what the FAA wants you to know about these. So the pilot has the ultimate responsibility for the safety of flight. Human error is actually one of that's the leading cause of aviation accidents. So far more than mechanical failures. So most aviation accidents are caused by human error. So that's why the FAA wants you to know about proper decision-making skills. And then recognizing hazardous thoughts is the first step to correcting them. Risk management relies on situational awareness, problem recognition, and good judgment. And then pilot fatigue is hazardous because it leads to a decrease in the ability to carry out tasks. So, yeah, question. Oh, yeah. So, what's the reasoning behind aileron and elevator deflection for taxiing, increasing the downforce for traction? Okay, I'll go back to that. The FAA basically says that it's so the wind cannot get under the wing and then flip the airplane. So if you have a up aileron on the left-hand wing, if you have a quartering headwind, then yeah, that would push the wing down and make sure that no excess lift is being produced. But then in the case of a tailwind, down aileron means that the wind isn't able to get under the wing and then produce a lifting force.
Yeah, a good way to explain it is if you have a airplane that's you have your airplane's flying this direction. If you have any kind of headwind like this, it's going to create more lift on both wings because you have more airflow over both of the wing. If it's any kind of crosswind like that, then the wing from the, I guess it's quartering headwind. So if the wind is a crosswind from the front of the airplane, it's going to cause one wing to create more lift than the other wing because there is more airflow on this side than there is on that side because this side is blocked by the body. So the wing on the right is creating more lift in that situation. The point is, it'll tilt the airplane. So it's used for taxi and for takeoff as well. You also hold it crossing direction. The idea is that if I'm taking off and there's a big crosswind and I don't do anything at all with my controls, my right wing is producing more lift than my left wing, and I'll just tilt over to the left. The point is that we're supposed to stop it by using aileron into the front. Then the reverse holds true if it's coming from the back. If it's coming from the back, it's pushing behind the airplane, which means that the airplane is producing less lift and less airflow. Since essentially it has to move through the airflow. And what that means is that if a quarter tailwind like this, that means the right wing is producing less than the left wing. The point is, if you have a tailwind, you want to, especially call it, dive away from the wind. So you go aileron opposite. So if we're come on into the wing, you go aileron opposite. So it's all just about one wing is producing more lift than the other.
Yeah, so common behavioral traps. The first one is scud running, and then this is when a pilot tries to maintain visual contact with terrain in low visibility. So this is essentially flying in IFR conditions when you're VFR, and that can get really dangerous because you can fly into a cloud. And out in Colorado, we can pretty easily hit a mountain, which would be pretty bad. Yeah, so flight into instrument conditions can cause spatial disorientation. I mean, it's actually incredibly profound. When you actually fly into instrument conditions, you'll notice it a lot more than like when I'm talking about it. But you can get really disoriented, especially because an airplane can move in pretty much it's free. It has 6 degrees of freedom, and so you can feel like you're accelerating when you're just tilted up, or you can feel like you're falling backwards when you're accelerating. I mean, you can have pretty profound spatial disorientation. So in the event that you do fly into instrument conditions, you want to trust your instruments pretty much 100% and just assume that they're correct, because your physical senses become extremely disoriented. So, and then another common behavioral trap is checklists are very often neglected. With airplanes, there are a lot of things to remember, right? Way more than driving a car. Like, so if you forget to flip a switch or turn on a pump or something, you could have some catastrophic failure. So that's it. Do you want to start your lesson? Yeah.
Really interesting.
Do you want to connect to this?
No, I'll just screen share it.
Yeah. Yeah.
Mute your Zoom, because if you take it. It's move that one.
Yeah.
Okay, so I guess the plan here is that now we're going to move on to talking about weather. weather is a very complicated section because not only do we have to talk about weather information, which is how do we actually pick up weather information, we also have to talk about weather theory. So it's kind of a two-branched lesson. We'll start off by talking about weather theory because it God damn it. There we go. We'll start off by talking about weather theory. Weather theory is easier to kind of grasp to begin with, and then weather information will make more sense once we talk about weather theory. So yeah, essentially weather theory is going to be, why does weather get created? You know, what are different factors that contribute to that? And then weather information is, how do we actually get that information when we're in the airplane? How do we interpret the information that we're given when we're in the airplane? You're killing me. God damn it. So we'll start out talking about weather theory. So we'll start out here. So first, let's talk about the atmosphere of Earth. So we'll start out by giving ourselves a ground here. And biggest things to understand, we have an atmospheric composition, pretty much the same atmospheric composition the whole way up, of about 78% nitrogen, 21% oxygen, 1% other stuff. And that's that same composition all the way up, except water vapor sometimes changed it. But the important things to understand, we have different layers to our atmosphere. The first layer of the atmosphere is going to be the troposphere. And the troposphere is going to go from the surface to about, well, depends on conditions, but somewhere between about 30 and 50,000 feet. So the troposphere is somewhere up here. And the troposphere has 75% of the mass of the atmosphere, because that's where all of the high density air is. So it contains most of the atmosphere, and not only that, but it's going to contain most of the weather, because it's going to have most of the water vapor and most of the different heating cycles and all that kind of stuff. So the troposphere is pretty much the main focus of this lesson, because that's where most of our airplanes are going to fly, and that's also where weather is actually going to happen. So we have that. Above that, we have the tropopause. And the biggest way to differentiate between the troposphere and the tropopause, when you're in the troposphere, as you go up, temperature goes down. So for example, like we go stand on top of Long's Peak, it's going to be colder on top of Long's Peak than it's going to be down here, just because as you raise in altitude, temperature goes down. Once you reach the tropopause, that stops happening. So that's how you understand that. And then above the tropopause, you have the stratosphere. Then above that, you have the stratopause. And then above that, you have the mesosphere. None of that stuff really matters. We don't care. We really just care about the troposphere. So if you want to learn about that, you can, but it doesn't really apply here. Questions on that? Okay. So now we'll go ahead. We'll talk about the idea of a standard atmosphere. I know we've already talked about this a little bit when we were talking about density, altitude, and performance, but we'll go over it once again. Standard atmosphere is essentially the idea of what an atmosphere would act like in, I guess, the FAA's view of a standard of a standard day. And pretty much what they're doing is the FAA is setting a baseline of, they're just saying this is a standard atmosphere. So that way you can make essentially changes to it to change, to adjust for temperature differences and stuff. So the FAA defines a standard atmosphere, and then that way performance charts and stuff can be made in reference to a standard atmosphere. And that way there's kind of an understanding of what that means. The FAA's definition of a standard atmosphere is different than like other definitions. So if you go to a meteorological definition, it may be different. The FAA has kind of their own one, and that's going to be 15 degrees Celsius at sea level, or 59 degrees Fahrenheit. And then it's going to be 2 degrees Celsius lapse rate per 1,000 feet. That'd be a negative 2 degrees. So, essentially what this means, and actually we'll also just throw in real quick, negative 3.5 degrees Fahrenheit per 1,000 feet. Essentially what this means, this is just the FAA kind of putting numbers to that idea of the troposphere. So like I said, as you go up in altitude, it's going to get colder. And this is the FAA defining that. So they're saying that in a standard atmosphere day, if you go up 1,000 feet, it's going to get 2 degrees colder. The reason for this is as you go up, pressure decreases. And from, ideal gas law, if your pressure goes down, your temperature is going to go down too. So essentially, the FAA defines that for every 1,000 feet you go up, temperature should decrease 2 degrees Celsius in a standard atmosphere. That means that at sea level, it's 15 degrees. At 1,000 feet, it's 13 degrees. At 2,000 feet, it's 11 degrees, so on down the line. Questions about what a standard atmosphere represents? Okay, so now we will talk about how weather is actually created in this atmosphere. So big thing to understand from the FAA thinks that all weather is created by temperature change. Once again, if you went to an atmospheric science thing, people would probably have a lot of different ways to define it, but the FAA is essentially right in that all weather is just a result of temperature being different than temperature somewhere else. Another way to define it is all weather is resultant from uneven heating of the earth. In order to understand where weather comes from, at a basic level, we need to understand why there's uneven heating of the earth, because we're running off that assumption that that heating is causing weather. And there's a bunch of different variations that are causing this. But most, I guess, easy to understand would be you have diurnal variation. Diurnal variation is just a fancy way of saying day-night variation. So during the day, we have heating, and during the night, we don't have heating. That's pretty simple. You have seasonal variations. And I would hope I don't have to describe this too much, but you have your sun, you have your earth, and your earth is not on a fixed axis. So when it goes around, sometimes the northern hemisphere is getting more heat, and sometimes the southern hemisphere is getting more heat. I hope we get how seasons work. So yeah, as your earth orbits the sun, seasons change. And the point is that you'll have more intense heating in the north hemisphere during the summer, in the northern hemisphere, and then vice versa in the summer in the southern hemisphere. We have latitudinal variations. Latitudinal variations are referring to being at a different latitude is going to give you different amounts of heating. So if you're up at the North Pole, you're going to get very little heating because all of the sun's rays that reach you are coming at a very strong angle. And so you get less heating per unit, if that makes sense. So if I have my earth here and I have my sun that's spraying out, rays of energy, the point is that the guys up at the North Pole have to kind of share, like the energy is spread over a wider distance. And so the point is that at the North Pole, it's going to be colder in general than it will be at the equator. And same up here, it'll be colder than it would be at the equator. We also have topographical variations. And this is the idea that if we're sitting here and we have heating of a, you have an ocean and you have land, Oceans have very, very good, I guess, thermal capacity, right? So because it's all water, it doesn't heat up very well. And then because the water is kind of mixing with itself, the heat also gets kind of pulled away from the surface. And so oceans generally will stay pretty close to the same temperature during the day and during the night, whereas land will heat up and cool down a lot because land pretty much doesn't move away and absorbs heat really well. So you have variation just from water versus land. You also do have altitude variation, which we kind of already talked about before, which is that idea as you move up, there's going to be less heat in the air. And that's the whole idea of that temperature lapse rate. Pretty much the idea behind it here is the temperature lapse rate we were talking about comes from a pressure difference. So as you go up, the pressure changes. Here, the altitude variation is the idea that if you have the sun heating the ground, then the ground will heat the air close to the ground, and it won't heat the air further from the ground, if that makes sense. So the air close to the ground will be very warm, hence uneven heating. Questions on any of these kind of reasons for why we get uneven heating? Okay. In that case, we will move to talking, I guess about, well, first we'll talk about pressure systems and pressure variations, and then we'll go into talking about some of the actual things that come from this uneven heating. So we'll put this aside for just a second and we'll talk about pressure real quick, and then we'll come back to it. So pressure varies with altitude, temperature, and density. Temperature and density and pressure obviously all affect each other due to ideal gas law. And then altitude, as you go higher, there's less air above you to push down on you. So you have lower pressure at higher altitudes. An important thing to understand is in our atmosphere that we just described, let's call that, so this is our standard atmosphere. In our standard atmosphere, we have essentially we have a certain height of the atmosphere. So the atmosphere goes up so far, and we'll call that a certain height. And an important thing to understand is if it were to get cold, so it was to get colder than a standard atmosphere, then everything would kind of compress, because the atmosphere would be less dense, and so the atmosphere gets shorter during the winter. The entire atmosphere kind of collapses a little bit during the winter. This is why you'll hear people talking about how the jet stream gets lower during the winter. We won't go too far into it, but essentially the jet stream runs like right at the top of the troposphere. And the point is that when winter comes along, everything gets colder and the entire troposphere just kind of like compresses on itself. And then on a day that's really, really hot, that's above standard atmosphere, you will get a kind of an expanded atmosphere. So one thing to understand, this is why, for example, in Florida, you will oftentimes get higher thunderstorms, and you'll get bigger, I guess, weather systems, like, I guess, taller weather systems. Whereas in some place like Colorado, until summer comes along, you wouldn't get that kind of vertical development, because the point is that when it's warm, that atmosphere is much bigger. There's a lot more room for things to happen. Whereas when it's cold, the atmosphere is significantly smaller. The important thing to understand about pressure is just a reference of how much air is above you, which means that if you're in this hot atmosphere, and your pressure is there, it would be the same pressure as those three locations across that atmosphere. The point is that the pressure will, like, I guess, the altitude at which you would experience the same pressure changes because the atmosphere is expanding or contracting a little bit. And this is a very kind of overdone thing. We're kind of embellishing how bad it actually is, but the point is, it's just to show why we have these pressure differences from temperature. But yeah, we have pressure systems, and pressure systems are essentially, they're essentially areas that have low or high pressure, and oftentimes they're associated with certain kinds of weather. So if you were to have a low pressure system, a low pressure is going to be just kind of a place that has low pressure air that's surrounded by higher pressure air. And it's generally associated with bad visibility and bad weather. So bad weather here. And it normally circulates inwards, upwards, and counterclockwise in the northern hemisphere. So inwards, upwards, and then counterclockwise in the northern hemisphere. And given that we're going to do all our flying generally in the northern hemisphere, I'm just going to not write that, but understand that in the southern hemisphere, these rotate opposite. The thing that we're trying to understand here is essentially you have a low pressure air, and what happens is essentially you have a low, and then you'll have, you know, high pressure. I guess I should, you have high pressure airs out here. And what ends up happening due to an effect called the Coriolis effect, which we're not going to get into too much, the air will spiral around this low pressure, like so. So it'll move counterclockwise and it'll push into the low pressure. And because it's pushing in, it's going to start pushing air up, because the air can't, you know, there's air getting pushed into that center part and it can't go down, so it has to push up. We'll talk more about why upwards moving air is bad here in just a second. So just kind of hold on to that thought, but understand low pressure is bad weather for now. Then we'll talk real quickly about high pressure. High pressure is going to be the exact opposite of low pressure. So it's just like this. And the point is that high pressure will go outward, downward, and clockwise. So outward, downward, and clockwise. So airflow wants to essentially go this direction, but it kind of moves like this. And so because the air in a high pressure is pushing out, that means that there's kind of a gap there, and that causes air to kind of fall down in the center. And then because air is pushing out, it's pushing out any kind of bad visibility and stuff. So we'll talk about it more here in just a second when we talk about convection. But the point is that high pressure is associated with good weather. So low pressure associated with bad weather, high pressure associated with good weather. And then high pressure in the northern hemisphere is clockwise, low pressure in the northern hemisphere is counterclockwise. Questions on that? What? Sorry, what?
You said the air wants to go upward. The air is going up.
Yes. Yeah, so essentially what's going on with low pressure, you have, the way to describe it, you have all these high pressures that are stuck, here we'll use our laser pointer. You have all these high pressures that are out around it, and then you have that low pressure in the center, and airflow is going to flow from high to low, because the high pressure air wants to get to the low pressure air. Because we're sitting on essentially because the Earth is spinning, it means that the airflow will essentially try to go directly towards it. So it'll try to run in towards the center. And there's an effect called the Coriolis effect. You can read up about it, but it's like when you throw a ball on a spinning, like thing, and it'll turn it right. The point is that it doesn't just draw a straight line in, it goes in a circle, but it slowly makes its way into that low pressure and it slowly tries to fill in that low pressure. And because there's all this air pushing in to the low pressure, then that means there's air in the low pressure and it has to go somewhere. And it can't push down, so it has to push up. Does that make sense? So you have air getting funneled into this one area, and when that air kind of comes together in that area, then it pushes up, it rises, because there's not space for all that air to come in. Does that make sense?
Yeah, but that, so whatever it's actually going up, is it already a high pressure? So it's like high and low, and then whatever it's actually down and up, that's high pressure again.
Yeah, I mean, it's I guess the way to describe it is the high pressure air is mixing with the low pressure air. I don't know if you could really describe it as, yeah, there being a, is it, I don't really know if you would describe it as a low pressure disappearing, because it's just some air is rising, but there's not like, it reaches a point where, yes, you would have so much air that comes in that eventually the low pressure would be replaced. And at that point, the low pressure would disappear. But while the low pressure still exists, then there will continue to be rising air until the low pressure disappears. Does that make sense? Until the pressure is equal. Okay. Any other questions? Any Zoom questions? Okay, so now we'll talk real quickly about convection, because convection is very important for us to understand kind of the creation of thunderstorms and some of these other things. So convection, plain and simple, is just the rising of air. That's, I guess, the way to understand it. And we're going to talk about, I guess, a bunch of different ways that convection happens. So it's the rising or descending of air is convection. So upward or downward movement of air. So we just talked about high and low pressures and how high pressure moves air down, low pressure moves air up. Generally, the way to think about convection is upward moving air is going to cause weather. Downward moving air is not going to cause weather. Reason for this is as air goes up, temperature is going to go down. And when temperature goes down, the air cannot hold as much water. And so as the air goes up, it'll reach a point where it reaches its dew point. And at that point, it becomes a cloud. So let's write this out. The idea behind most of the idea behind convection is essentially you have an air parcel down at the surface, and the air parcel gets risen up, the air parcel gets moved upwards. And when that air parcel gets moved up, it's going to get colder because it's going to expand. And as it expands, it's going to get colder due to essentially the pressure being lower. And when that parcel goes up and gets colder, eventually it'll reach its dew point. So eventually it'll reach the point where it creates this cloud, or essentially where it creates water. And so then you'll have a cloud that gets created inside of your parcel. So parcel goes up, it expands, it cools down, and it creates a cloud. And then if it continues to get pushed up, eventually it'll start to precipitate and it'll start to rain from that. So you'll start getting rain out of it if it continues to get pushed up. And the idea is that a high convective activity day is where a lot of these parcels are getting moved up into the air, and they're creating a lot of essentially upwards and then downwards movement when they rain. We'll talk here real quickly about a few of the things that can cause it. For one, low pressure and high pressure can cause it. So low pressure, one of the reasons why it's associated with that bad weather is it's lifting up this air. And when that air gets lifted up, it becomes a cloud. Another big thing that causes is just the diurnal heating of the ground. So during the day, we're going to get the sun that comes out, sun beats down on the ground, heats the ground up a lot. So now the parcels of air that are close to the ground are going to get really hot. So if I'm, investigating these parcels of air that are down close to the ground, it could be as hot as, let's say they're 98 degrees Fahrenheit. Actually, let's not use Fahrenheit. Let's say they're like 30 degrees Celsius. And the point is, the rest of the atmosphere is colder than that. Because that air has heated up at the ground and it's warmer than its surroundings, the air is going to move up because hot air rises. And it will move up until it, becomes the same temperature as its surroundings. If you have a day where there's really, really aggressive heating at the ground, that air will move up and it will hit its dew point before it becomes the same as its surroundings. And at that point, it'll form a little cloud. So good example of this is pretty much every day in the summer in Colorado, you will see the ground heats up about 8, 9 o'clock. You'll see gliders that will get in the air and they'll ride these parcels up. And then you'll start to see clouds and stuff forming around like 10, 11 o'clock. And they will continue to form through the day until like 1 o'clock, 2 o'clock, where there's so much air rising up that eventually those clouds start to form thunderstorms. And those thunderstorms precipitate back out on us. And that's pretty much the basic idea of what convection is. That's what convective activity is you have heat at the ground, heat moves up, and if you have enough energy, that heat will move up and cause precipitation in an area. Questions about that? Okay. We can also talk about a few other causes of convection, but just understand, really it's this heating that's causing most of like convective activity. When you think of thunderstorms, it's this heating that's causing most of it. But there are a few other causes that are worth knowing. I cannot write. We have valley breeze and we have mountain breeze. And this is the idea that I have a mountain and a valley. Generally, those go together. And as a mountain gets warmed by the sun, adjacent air is going to be heated faster. And so there's going to be kind of a wind that's flowing up the hill. What does that mean? That essentially means that so let's say that the sun, in our case, the sun is in the southern sky. And so let's say that this is pointed kind of south, if that makes sense. So the sun is in the southern sky and is kind of hitting the southern side of a mountain. That means that it's going to heat up that entire side of the mountain. And when that side of the mountain heats up, it will heat the air next to it. So the air here is getting heated. Like all these parcels are heating up. And the point is, when those parcels heat up, they rise, and that causes air to have to kind of funnel in. Well, that causes air to have to funnel in here to replace that heated air. So that heated air starts to rise away, and that causes air to funnel in here, which will create a lifting up the slope. It's useful for glider pilots because they'll sit right at the top of one of these and they'll get pushed up by that. And I guess it's worth knowing that the side of a mountain that's getting heated will have a little bit of an upslope wind. Then mountain breeze is the exact opposite. It's the idea that the mountain will lose heat faster, and so the mountain will essentially cool down faster, and you'll have the exact opposite. So you'll have a bunch of parcels in here that cool down quickly, and then they all want to fall down the mountain. So at night, everything falls down the mountain, whereas in the day, everything goes up the mountain. Not really that big of a deal, but worth understanding. Questions about that? Okay. And then Another one that's worth talking about, well, there's a couple more things that are worth talking about here. There's land sea breeze. And then we'll also mention very briefly mountain wave, mostly just because it happens in Colorado and I think it's interesting. It's not really going to be on the test. But land sea breeze is the idea that the water and land, like we said before, water heats up differently than land. Land will heat up more than water. And so you'll end up during the day, you'll have your water there, you'll have your land here. The land will heat up, you'll get a bunch of heat here, the heat will rise, and then generally it'll flow out towards the ocean, and the ocean has a bunch of cool air that kind of flows like this. So you just get breezes that come in from the ocean during the day. And then at night, the flow reverses. The ocean doesn't lose heat, whereas the land does lose heat. And so suddenly the ocean will be warmer than the land. And then all the air will blow out towards the ocean. These kinds of effects are pretty small. They're not really that big of a deal, but they might show up on your test. So that's why we have to teach them. But yeah, like have I ever used, land sea breeze? No. Do I understand it? Maybe it's a good thing to understand if you're close to the ocean, but relatively small topic. Questions on any of that? Okay, and then let's just talk very briefly about mountain wave. Just to clarify, mountain wave will not show up on the test. Mountain wave is not a tested thing.
I think it might.
It's not going to be tested in the way I'm describing it. I'll put it that way. This is purely because we live in Colorado, which is one of the epicenters of mountain wave. And it's a good thing to know around here if you plan on flying around here. But it's certainly not a very tested topic. Okay. We're going to pretty much look at this. This is Grand Junction out here. That is the worst writing I've ever done, but whatever. This is Boulder out here, and then here is like Breck. So this would be your ski resorts, your mountains, whatever. We're very ultra simplifying it. Point is, you have airflow that's coming from Grand Junction. That airflow is probably pretty cold. It's probably going to be, let's say it's 10 degrees Celsius. And you have that wind, normally it's getting pushed out in front of like a front. So you have some front that's pushing this direction and it's pushing that air in front of it. When that hits the mountains, it rises up the side of the mountain. And as it rises up the side of the mountain, it begins to cool down. Once it hits a certain height, it hits its saturation point. And at that point, begins to, create clouds, drop precipitation. But that's why we have such good skiing conditions here, is that you have that big flat area, that big flat desert. It all pushes up, comes up the side of the mountain and precipitates all over our ski resorts. So we have that. And the point is, when that precipitation comes out, the precipitation essentially, it gives energy back to the air because it's turning from a gas into a it's condensing. And what that means is essentially the air doesn't cool down as much as it kind of continues up the mountain. So the point is, when you hit your when you hit like the area where saturation happens, let's say you're at like 2 degrees Celsius. The point is that the air starts to cool slower at that point, because as the water precipitates out, it warms the air a little bit. Then you get up to the top of the mountain, and let's say that you're at like 0 degrees Celsius. The point is, as that air starts to fall on the downward side of the mountain, it falls and it heats up at a speed that's equivalent to where this was. I guess it's the lapse rate of heating is equivalent to the lapse rate of cooling before it's saturated. The point is that it unsaturates immediately as it starts falling down the side of the mountain. And the point is that the air, when it reaches the boulder side of the mountain, is going to be significantly warmer than it was at the Grand Junction side of the mountain, because it's essentially it unsaturated immediately during its descent. So it'd make more sense if we were atmospheric science majors, but we're not. And so the point is, you essentially have warm air that's coming down to Boulder because you go up on the Grand Junction side. And essentially, I guess the best way to understand it is when the water precipitates out of the air, it kind of gives the air more energy, which means that when the air comes back down, it's warmer. And the thing to understand is this causes very, very violent convective activity in Colorado during the winter, because you have these big storms that are pushing towards us. They push all this wind over the mountains. And when that wind comes over the mountains, it all heats up a lot. And when it gets to the Boulder side of the mountains, it's all very, very warm compared to the rest of the air. And then it starts to rise on the Boulder side of the mountain. All right, so it came down here, it's like 15 degrees Celsius, but you know, the airflow that never hit the mountains, the airflow that just went over the top of the mountains, let's say it was like, 0 degrees Celsius, it's still 0 degrees Celsius. And so the point is that 15 degrees Celsius air is kind of superheated, and it just kind of goes into this massive rising thing. So you get these really massive rising air around here, and it'll go way, way up in into the atmosphere. And then sometimes it'll get energized by the jet stream during the winter. And then it'll come back down, and you end up getting these massive waves of air flow moving up and then moving back down. You don't really have to understand all of this stuff. All of the stuff that comes here doesn't really matter for a pilot. It's kind of cool for an atmospheric scientist, but it doesn't matter for a pilot. The things that do need to be understood are here in Boulder, we get these massive, what are called mountain waves, where you get significant amounts of upward and downward movement of air, which can be very dangerous to people. Yeah, small tangent on how mountain wave works. If you ever get any of those days, which we already had one like 3 days ago, where you get like 88 knots of wind coming off the mountains, you're going to expect that you have very severe updrafts and downdrafts. So you would have very, very severe turbulence if you were to fly into Colorado at that time. Questions on mountain wave? Once again, it's not tested, just kind of a tangent that I figured we'd cover.
But why is it still, I mean, if it's warmer, then you just survive, like, why does it come back down and go back up?
So this is one of the things about it being in the winter, but essentially it's that the air is so warm, and it goes up into the atmosphere, into the high atmosphere, and then because the atmosphere is kind of shrunk by the because it's winter, everything's colder, you have a lower jet stream, and the jet stream carries very cold air. And the idea is if it can get into the jet stream, then it'll continue to go up very, very high. And then once it reaches an altitude, it becomes, I guess, it has all this energy where it's pushing up really, really aggressively. And once it gets up to that kind of altitude where it finally levels off, then it's become too cold, and then it starts to drop down on the backside. And then you get this cycle of it going up and down, because it has so much energy that it kind of overwhelms the, it doesn't stop where it's supposed to stop. It continues to rise through it. Yeah, exactly. The momentum takes it through its, I guess, stopping altitude, if that makes sense. Yes.
Say, I don't use situation for one.
Mhm.
And so that gives that representation.
Yep.
Let's say it's not something right now, it's like where, I mean, it's not, the lab rate is, it's, because it's losing heat in the atmosphere, right, the upper level of the atmosphere. When it's coming back down, it has to warm up, it's not, it's picking up somewhere.
No, it's the pressure is increasing and it's getting heat from lapse rate. Right, the heat is purely coming from the fact that as it descends the mountain, the pressure increases because it's lower in the atmosphere. And if the pressure increases, it gets squished together. PV equals nRT. So
Yeah, it's only if B is constant, you have. I don't know. Yeah. I guess it's probably just-
sorry, so as you drop down the mountain, temperature will increase because pressure increases as well. Does that make sense?
I'm sure we can in volume with someone else. Volume is shrinking as well, because of the pressure around it, then you may not necessarily have.
Well, sure, but the point is, you have your lapse rate, and you follow essentially here. You're following what is it? You're following an unsaturated lapse rate. Here, you're following a saturated lapse rate, and the point is that you instead of like on the dropping side of it, instead of using a saturated lapse rate here, you're using an unsaturated lapse rate the entire way down. And so the point is, that's where the heat's coming from. I can't give you the thermodynamic explanation of it, but the atmospheric science definition of it is that the heat comes from that difference in lapse rates.
That big air mass, then the issue is.
Because it's warm, because it has all that extra heat from that lapse rate change. And then as it rises, you'll get updrafts in excess of like 4,000 feet per minute. And so there's these massive rising things. And that's why that momentum carries it through its altitude. And that's why it's, like you said, an undamped system where it goes up and down and up and down. So you can kind of look on days, they're called wave days. You can see the layers based off of where clouds form, because at the tops there will be clouds, and there'll be essentially standing lenticulars, or what they're called. So there'll be there's wave like cap clouds, and then there's standing lenticulars. Standing lenticulars represent those, like where those tops are. And essentially they're those ones that kind of look like stacked clouds. Like they just look like they're stacked on top of each other.
You can put it up if you want.
Yeah, that would help. And normally you have your primary wave would be like maybe 10 miles away. And then you would be in like another 10, 20 miles to your secondary wave. And then, you know, another 10, 20 miles to your tertiary wave. And those are like the main waves that you would actually be able to see. But then that will continue on, you know, it can continue on for many hundreds of miles. So once I took a 150 out to like Florida, and when we were in Kansas, you could still feel like these little, but they're very small, just little adjustments. So as you fly out, you would be in airflow that would be moving like 50 feet per minute up, and then you would be in 50 feet per minute down. So you kind of get like these really small alterations. So it has a very severe effect on atmosphere for, you know, hundreds of miles past it, but the actual place where it applies most severely would be within like the first 50 miles from that location, which is why in Denver it happens a lot, where we get very severe mountain wave. But does that make sense? Once again, not really on the test. I just figured it was worth talking about because of our proximity to it. But
This is mountain breeze.
yes, mountain breeze is just, hey, it heats up, you know, the entire side of a mountain, and so because of that you get a little bit of a breeze. This is very high energy, different kind of thing. Yeah, also, if one more way to understand, it's not actually that the hot air is rising. If you want to actually understand it, it's that you have hot air and the cold air is sinking through it. So the cold air sinks down and forces the hot air up. It's not hot air rising, but it's easier to visualize it that way. But
So if you just span that to your mountain face and valley, so and part of the definition part of the value where it heats up and you get the top. So what's the problems?
At night, the ground cools down faster than the air. And so you get a downdraft because the cold air is close to the mountain and then it falls down the mountain.
So you get a down at the same time.
Yes, you would get a downdraft. Well, you would get a downdraft anywhere that had a valley, if that made sense, because all of the ground would, I guess, reduce heat. So it wouldn't just be on the sun side, if that makes sense. But anyway, now we talk, we'll talk real quickly, wind shear. I'm on my laser. Wind shear is pretty much just the idea of wind that isn't that's changing. So it's a bunch of different reasons that you can have wind shear. But essentially it's wind that's not all flowing in the same direction. Wind shear can be dangerous to our airplanes because when we fly, through wind shear, it changes the amount of airflow that the airplane is getting, which can be dangerous to the airplane. We'll talk about it here more in a second when we talk about things that can cause it. But for now, we'll move on to talking about clouds, fog, precipitation. We've already talked essentially about how clouds are formed. You have a temperature dew point spread as you go up in the atmosphere. That temp dew point spread will get closer together and clouds will form. The other option is, instead of things rising in the atmosphere and having convective cloud activity, the other option is just the temperature decreases for some reason or another, and that can cause clouds to form because low temperature means that the dew point comes as well. Generally, in Colorado, we're going to see mostly convective cloud activity, but obviously in a lot of other places, there's fog and stuff that comes from things that aren't convective activity. And the main thing to understand is if your temperature and your dew point are close together, you will find clouds or fog, whatever you want to call it. Because essentially it's meaning that you're close to your saturation point. Alrighty. Do you know if we have to know different types of clouds?
Yeah, I think you do. With like basic, well, just like basic cumuliform and stratiform and stuff.
Really?
It's pretty gross.
Really? Okay. You want to describe clouds?
I didn't prepare for that.
Okay. I'll describe clouds. I hate clouds. Okay.
We all hate clouds.
So I guess we have to know different kinds of clouds. There's 3 different kinds of clouds. There's high clouds, middle clouds, and low clouds. I'm not reading off of anything here, by the way. I definitely knew these because of course I would. Why wouldn't I? Cirrus is definitely high clouds. And then you have alto clouds, which are middle. Come on. What the? Okay. Middle clouds. And then you have I guess stratus clouds, which are low clouds. And there's a bunch of different types of these, but we're not really going to go into that because it doesn't matter. If you really care, you can go search them up. But the biggest ones that we want to understand are towering cumulonimbus. Towering cumulonimbus is the way that we describe clouds that are developing vertically into a thunderstorm. So if you see very large towering clouds, it's a cumulonimbus cloud. So if you see towering cumulonimbus clouds, you know that there's a thunderstorm developing. We'll talk about here in just a second why that's a bad thing and what thunderstorms have. So yeah. That's kind of the biggest thing to understand. I'm not going to go through all the individual types of clouds because I don't care. Yeah. We also have a bunch of different types of fog. That we have to know. Types of fog. We have ground fog. Ground fog is just fog that apparently covers the 20 feet closest to the ground. So if it's less than 20 feet deep, it's considered ground fog. And we have radiation fog. The idea behind radiation fog is, let's say that you live in a very humid place, and you have a clear night, like a night that has no clouds. All of the heat from the ground will radiate into the air. Well, I guess not into the air, but it'll radiate away from the ground. And the point is the ground will cool down very quickly, and then the ground will cool the air above it to the dew point, and you'll create fog at the ground. So radiation fog comes on cloudless nights. That is the question that you will get asked about radiation fog on your test. Between, I guess technically radiation fog can be ground fog. Ground fog is just fog that's within 20 feet of the ground. There is no talk about how it's created. So they could interchange with each other. Advection fog. Advection fog is essentially where you have what we talked about of you have a thing like your land sea breeze here. And the point is that at like, I guess if you're on the coast, you might have moist air from the water that gets pushed over a colder surface. So at night, moist air comes from the water, gets pushed over the land, and it'll create fog just along the coast. You have upslope fog. Upslope fog is best understood as air gets pushed up a mountain and it becomes fog, and so you just have fog that sits on the side of a mountain. And then that's pretty much all that we actually have to apply from that. Questions on clouds or fog? Good, because I can't describe it any better than that. Okay, we have a few visibility restrictions that we have to know. Essentially, if you have haze, which is just a bunch of particles that are in the air, you have smoke, like from fires, you have smog, which is fog and smoke, and then you have dust and volcanic ash. If any of those are in the air, they can reduce your visibility. We don't really deal with that out here very much. And this is also a good time to go back and remember low pressure systems are associated with poor visibility because low pressure systems generally have all that air pushing in, and that brings in all of those visibility reducing particles and kind of puts them into that low pressure area. But yeah. Alrighty. I really don't want to talk about fronts either. I hate weather. I hate weather with a passion.
Most pilots absolutely hate weather. That is definitely a common theme.
Yeah, the I guess the part about weather that's kind of interesting is that it's hard to kind of get a good grasp on weather unless you look at weather over a long period of time, because at the end of the day, like, pilots are kind of expected to be meteorologists to a degree. So you have to kind of look at weather over a period of time and study it more than just a little bit. But for the purposes of this test, we can study it just a little bit and we'll be fine. So anyway, we're going to talk about frontal activity. Frontal activity, you have a cold front. Cold front is where a cold air mass overtakes a warm air mass. And the cold air is more dense, so it'll slide under the warm air and it'll push the warm air up. So you have cold air, and this cold air essentially will kind of come and slide under warm air. This is a very terrible drawing, but the main things to understand are because it's pushing that warm air up, that warm air will lead to a storm. So you'll end up getting precipitation normally in a cold front because of that. A warm front is when a warm air mass overtakes a cold air mass and the warm front slides over the cold front. Once again, you're going to end up getting storms because warm air is getting pushed up. A stationary front is when a cold and a warm front move in and just kind of hit each other. And essentially it's considered stationary because they're not moving. They're just sitting there next to each other. And once again, a stationary front can still produce storms off of a stationary front. That's all we really have to know about fronts, is that they provide storms and that, you know, you have warm air overtaking cold air and going on top, or you have cold air overtaking warm air and going underneath. So, and then technically you have an occluded front where, I guess two fronts kind of move together, but we're not going to worry about that too much. Questions on fronts? Okay. Sorry, what? Probably not for, yeah, I would imagine not on the private test, no. So, we will talk briefly about thunderstorms. So we'll talk about thunderstorms and why they're dangerous to aircraft. So thunderstorms, big things to understand. There's 3 stages to a thunderstorm. There's the cumulus phase, there's the mature phase, and there's the dissipating phase. The cumulus phase is a phase where you have those cumulonimbus clouds that are rising. And so you have essentially those towering cumulus clouds. The mature phase is where the I guess the thunderstorm has risen enough and it starts to create precipitation. So where it has precipitation, and that's going to be where you have significant updrafts and downdrafts. The cumulus phase, you're going to have significant updrafts only because it's still building up into the air. And then the dissipating phase is the third one, and that's where you have generally just downdrafts and all of it's kind of falling back down to earth. You're going to have a lot of issues that come in from dissipating phases because you get what are called gust fronts and microbursts and stuff like that. So we'll talk real quickly about that. Essentially what happens is you have your dissipating thunderstorm. So you have your big towering, you know, cumulus stuff, and then you have where it starts precipitating out here. And the point is it all precipitates down, all that air pushes down, and then it pushes out. And you get these very aggressive gusts of wind that are pushing out in front of the actual rainy part of a storm. And if you were to fly through that, you would be, you know, you would end up having severe turbulence and severe wind shear because the wind would change very abruptly from, if you're on this side, the wind would be coming this direction, and then obviously it abruptly change to a tailwind when you fly through to the other side. A microburst is essentially what we're talking about here, but on a very small scale. A microburst is a very small scale where there's a big dropout of precipitation. So a microburst is essentially a very small scale thunderstorm. And the reason they're very dangerous to aircraft is they're going to have all that air pushing out in all directions. And if you were to fly into a microburst, you would have a really big headwind, and then it would push you up. And then after you got out the opposite side of a microburst, you would have a very big tailwind, which would oftentimes result in a stall. So microbursts are very dangerous to us. Big thing to understand is microbursts come from thunderstorms. And yes, you would have a downdraft in the microburst as well. Although generally that's not the problem. The problem is that your wind is coming at you to start with. So if, you know, I'm flying my airplane with a 65 knot approach speed and I get 30 knots of wind off the nose. So I'm flying here and I get 30 knots of wind pointed at me, then I'm going to slow myself down to like 35 knots of ground speed. When I get to the opposite side of the microburst, suddenly that wind switches from being on my nose to on my tail. And so suddenly I have to be going 60 knots faster in order to reach, in order to not, like, I guess, in order to be at my approach speed. So I come in on the microburst, I have 30 knots of headwind, and then as I go out the other side, I have 30 knots of tailwind. And that's oftentimes what'll kill people is the abrupt switch from having a severe headwind to a severe tailwind. So that's why microbursts are dangerous.
Is there a way to recover something? I guess you come out in your airspeed.
Yeah, you would be fucked in that scenario. That's also a very aggressive scenario, but no, if you're in a microburst, I mean, the only way to identify it would be to understand that, like, to realize, like, you get a big gust in front of you, to realize you're going to lose it. So instead of slowing down, just keep the power in and but yeah, the point is you can get out of a microburst if you know that it's there, but if you didn't know it was there, it's hard to get out of, which is why we don't fly in thunderstorms very much, because they're very dangerous. So
Yeah, I mean, like, generally, you're not gonna, like, microbursts are only gonna be occurring in pretty bad weather, and you're not gonna be flying in bad weather. And then, like, at least on a small airplane, and then big, like, commercial airliners have, like, really cool computers that do, like, wind shear alerting. So, like, they'll be able to tell you when, like, you have wind shear and stuff. I mean, that was, like, a mandate after, like, 1987 or something.
yeah,
for
they
commercial
crashed a
airliners.
few airliners because of microbursts, and then
Yeah.
suddenly they had to fix it.
So yeah, I mean, big airliners have like some cool computers and stuff.
That does get to our next topic, which is how we avoid thunderstorms. And you avoid thunderstorms by staying 20 miles away. If the FAA asks, I don't know. I don't think anyone, let's put it this way. If you're a glider pilot, you don't stay 20 miles away from thunderstorms. It just doesn't happen. But if the FAA asks, 20 miles is the number that they want us to say. So you want to stay 20 miles away from a thunderstorm. That'll should keep you well clear of even the worst thunderstorms. If you do inadvertently get into a thunderstorm, you want to get through the storm in minimum time and get out of it. You want to have anti-ice equipment on if you have it. And you want to be careful about, you essentially want to maintain a constant attitude and get out of it as best you can and be prepared for a lot of turbulence. And don't mess with your power settings and stuff, because that will help you if you were to get into a microburst. But you shouldn't ever inadvertently get into a thunderstorm, especially not in the modern day. It's pretty hard to just accidentally stumble into a massive thunderstorm. So I don't know. Yeah. Questions on thunderstorms?
You said it's pretty hard, so I'm guessing you're basing it on forecast and weather information.
Well, no, you can also just look and see these I mean, if it's a massive towering thing, and then if it's at night, you'll see, huge lightning things. It's pretty hard to get into it. We also do have what's called FISB, which is flight information service, which will essentially tell us where precipitation cells are.
Yeah,
So,
I mean, you can see like they broadcast like through ADSB, they broadcast weather information, and I think it's called like NEXRAD or something. And then in most modern airplanes, you can see pictures of like precipitation density. So I mean, if there's like a big red spot on your map, like, don't go there.
So you have to.
Yeah,
so we
mean-
have them in the plane. The other one is you can talk to air traffic control, and they have radar. So even if you weren't to have those displays, you could ask them to keep you clear if it was at night. During the day, it is very obvious where thunderstorms are, because they're massive towering things. But yeah, actually, yes, but not if you're in it, right? If you're in it, it's coming from above you, and most airplanes don't have the visibility to see that. But if like you can actually see like little things kind of falling out.
Yeah, so this is a modern like display system, and this is like a precipitation density map. So if it's like really dark red, like don't go there because that's a thunderstorm. So I mean, this is something that's probably in like a Cessna 172. So I mean, you have access to information.
Here, let's see if this will work. What if I do work as intended? Okay, this is a picture that I took from my airplane flying out of Cheyenne. Not going to comment as to whether I was 20 miles away from that thunderstorm, but you can see massive thunderstorm, and you can see kind of this is like that way up there at the top is the actual like towering cloud, and then all of it below it is precipitation. So this is all just rain falling out of the bottom of the cloud. You can see it's very obvious that there's a thunderstorm there. So for any large scale thunderstorm, it'll be, I mean, well, even for small thunderstorms, it becomes pretty obvious once you're actually there. But yeah, you kind of have to be in the airplane to understand it, if that makes sense. You have to be in the airplane to see it. But alrighty. Lastly, for this, we talk about icing conditions. Biggest things to understand: icing reduces lift on the wing, because if ice builds up on the wing, it makes the wing not shaped, I guess, in the shape that it was designed. And there's a lot of dangerous things that can come. There's all kinds of conversation about tailplane stalls and blah, blah, blah. That doesn't matter. We're not worried about that because we aren't flying in icing conditions. Icing conditions are essentially going to be any time that it's below freezing and that there's visible moisture in the air. So the only time where we even legally would be allowed to would be like if you're flying in rain and it's below freezing. But even then, you're pretty stupid for doing that. Any other time, like if you're flying through a cloud or whatever, at that point, you're instrument flying, and that is outside the scope of what we do as private pilots. So we don't really have to, I guess, we don't really have to focus on it too much, but the biggest things to understand are icing is very dangerous to the aircraft, and we're not allowed to fly into known icing conditions, which means that we should, if it's near freezing, we need to avoid all clouds, all precipitation. And yeah, questions on icing? Okay, questions on anything we've covered so far in weather? Because we're going to move on here to weather resources. Alrighty. Now we get to shift gears and go to everyone's other favorite lesson.
I love
Which is
love
weather
interpreting
resources.
tasks. I love it. It's
Yeah.
so fun.
I love that we have to do it for the test too. I'm shocked that we have to do it. Okay, so we're gonna go back here. Now we're on weather information. So we talked a lot about how things get formed, how there's this, how there's that forms. Weather information is now how do we actually describe the weather that's around us, and then how do we, figure out from our resources whether we should go fly, whether we shouldn't go fly. So yeah. There's a bunch of different resources that we have as pilots in order to figure out whether we should fly or not. We have, what is it? Aviationweather.gov, is that?
Oh, yeah,
Yeah, okay.
that pretty much has everything. And then there's 1-800 weather brief.
Yeah.
It's like it's just.
Okay, so we have aviationweather.gov, we have 1-800-WX brief, and then we have ForeFlight. And essentially, we can use these resources in order to find weather. And beyond that, damn, it sucks in Wyoming, doesn't it? Want to go fly to Wyoming?
Yeah, so this just has a bunch of charts and stuff.
Let me explain the charts. But we'll do that here in just a second. Biggest things to understand, aviationweather.gov is online website. Anyone can access it. It's put out by the FAA in tandem with the National Oceanic and Atmospheric Administration, or NOAA. And then essentially 1-800-WX brief is a phone number and a website. And it essentially puts you in with flight service, and flight service is a company that's hired by the American government.
It's run by like Lockheed Martin.
Of course it is, but what flight service does is essentially they can give us in-flight weather advisories, so you can talk to them on the radio. There's certain frequencies you can use to talk to them. They manage flight plans for VFR traffic, and then they will also help us on the ground. When you're planning it out, you can call a weather briefer at 1-800-WX brief, and they will give you a weather briefing. And then ForeFlight's very popular app that's used, and you can find essentially all of the same charts that you could find on aviationweather.gov. ForeFlight's also subscription based though, so aviationweather.gov is the free way to access all of those charts. There's a lot of different charts and a lot of different ways to describe things. The biggest, I guess, way that we're going to break things up, you have weather reports, you have weather forecasts, and then you have I guess, well, yeah, that's pretty much, you have weather reports and you have weather forecasts, and then you have weather charts. And then you have in-flight weather stuff as well. And those are kind of our four main groups that we have to actually look at. So yeah. You have in weather reports, that's going to be current weather at certain places. That would include what's referred to as a METAR. It would also include speci METARs, and then PIREPs. Don't worry, we're going to go over all of these, but we're just writing them out first. And recently, TALPA, the Vicon stuff. Well, I guess you'll get to learn here. Okay, so METARs are normally released at hour plus 55 minutes, but they're sometimes released more often than that. What that means is they're released every hour on the 55th minute of the hour, if that makes sense, or approximately that. So METARs are essentially going to have a whole thing where they talk about where they are, what the time is, and then they're going to have wind visibility, runway visibility, and all kinds of that stuff. What can you pull up the METAR description and we'll just walk through it? Oh yeah, I guess you can actually pull the real one up. That would work. Yeah, fine. Hold on 1 second. You're in Wyoming. Is Colorado. Sure, Colorado's very close too. Okay, so METARs are represented in this way. essentially, it'll say METAR, so you know that it's a METAR. METAR stands for meteorological report, by the way, something along those lines. It'll tell you where it is. So in this place, it's KDEN, which is Denver International Airport. It'll tell you when it was put out, and it does this in Zulu time. So essentially what it tells you, the first one is what day of the month it was put out. So it was put out on the 4th day of April. We'll get there because it's the 3rd day of April. But the reason for that is because it's Zulu time, and Zulu time is going to be like England Greenwich Mean Time. And the reason they do that is that way we don't have to worry about time zones and stuff. We just do it off Zulu time. And because they're 6 hours ahead, it is the 4th day of April for them. And then this is the 4-digit, it would be military time. So it's a 24-hour clock. And the point is that it is 0053 Zulu is when it was put out. So that's the time. So where it was put out, KDEN, and then time 040 or yeah 00353 Zulu on the 4th day of the month. It tells us what the winds are. So winds at Denver currently are 280 at 18 gusting 23. 280 means that they're coming from a 280 magnetic heading. All of the METARs are in magnetic heading. So it's coming from a 280 heading, so nearly west, and it's coming at 18 knots, gusting 23 knots. Then it tells us what our visibility is. So currently 10 statute miles of visibility. The highest value for a METAR is 10 statute miles, so they'll never report more than 10. It'll always just be 10. I'm sure on a day like today, we have much more than 10 statute miles of visibility. Then it tells you where your cloud layers are. So your cloud layers are scattered at 10,000 feet and broken at 20,000 feet. Your cloud layers are all given in above ground level figures. So that means that if it's scattered at 10,000 feet, the clouds are actually at 15,000 feet MSL. So they're all above ground level from the station at which the METAR was recorded. Then we have temperatures. It's 10 degrees is the temperature, and -2 degrees is the dew point. So that's the temp dew point thing. And then here you have an altimeter setting. Altimeters 29338 would be the altimeter setting. And then they have remarks in here, and remarks are always tricky because no one ever knows what they mean. For example, AO2 means it is a precipitation discriminator, which means it can discriminate between snow or rain or whatever. Don't worry, I don't think we have to know what AO2 means, but yeah, the point is that means it's a precipitation discriminator. And then here it tells us peak winds, what the peak winds were. I don't actually know how to read that. It gives us sea level pressure. Sea level pressure and altimeter setting are actually the same thing. It's just sea level pressure is given in millibars for people who are flying airplanes from Europe, because it's an international airport. So that's there for people that would use that. We would never use that. And then they give a more accurate temperature here. So they're saying the temperature is 0100, which means that it's 10.0 degrees. And then this is kind of acting as a space. And then 1017 means that it's -1.7 degrees is the dew point. They give like more accurate versions of all the stuff that they gave above. Point is, the remarks section, you can never really guess what's going to be in a remarks section because they just kind of fill it with whatever, you know, remarks are for that station. But this stuff up here above the remarks section will always be the same for a METAR, no matter what station you're at. Can you find Boulder?
Is this for ground level at the station, like all the, for example, the Spanish static is that at ground level?
Yeah, that's at, so this is really would be the way you can consider it's from the tower at Denver. Sea level pressure, altimeter setting.
Yes, sea level pressure. Sea level pressure is Isn't that a standard thing, so one, then whatever, 101 or something?
Yeah, so pressure will change, you know, a little bit, and the point is you have to calibrate your altimeter. You have to, right? So pressure from day to day will be different at a location. And the point is, in order for altimeters to be accurate, because at the end of the day, all they are is just measuring pressure, we set them to a certain altimeter setting. So all that altimeter setting is giving you is that's going to say, if you set it to this altimeter setting, you will be accurate at the ground at Denver. That's all they're saying. So that altimeter setting is just used to adjust your altimeter to make it accurate at ground level at Denver. So
So it's not, so 9.4 is not actually the pressure at sea level, because there's-
so
It might
there
be.
is no, there's no sea level here.
Yeah.
The point is that it would be what the sea level pressure would be in order to make Denver at that height. Does that make sense? So Denver's at like, you know, I can,
what I'm trying to-
yeah, Denver's at a certain altitude. And the point is that we find Denver's altitude, like I guess if I were to just set my altimeter like to 2992, which would be a standard pressure day, it might be inaccurate. And so that altimeter setting is used to calibrate your altimeter. That's all you would use it for. But anyway, we'll go over the Boulder one just real quick. METAR from Boulder. This is your time. So fourth day, 0135 Zulu. One of the things to understand about any place that is an automatic weather system is that METARs come out significantly more because they're automatic. So no one has to check through them or anything. So it's easier for them to just kind of spit out a lot of METARs. It says here that it's auto. That means that it's an automatically produced one. So Denver, they actually have somebody looking at it. Obviously, it's still probably coming from a computer, but somebody looks over it and makes sure that that's accurate. Here, it could be completely inaccurate for all we know because it's automatic. So it's just kind of a word of caution, but normally they're pretty good. Winds coming from 330, so coming from the northwest, 12 knots, gusting 20 knots, 10 statute miles of visibility, scattered at 11,000 above ground level. And then 10 degrees, -2 degrees is the temp dew point. And then altimeter settings 2940. And then you can see here in the remarks, it just says it's a precipitation discriminator. That's all it says.
Do you talk about the dew point and why it's relevant to us one?
Oh, yeah, so the dew point is basically just like the temperature at which the current parcel of air would have to be cooled down to for it to have 100% humidity, right? So, and then if you cool it down below that, then the humidity is over 100%, right? So then that would mean that like water would precipitate out of the air and then fog would form. So
What the point is, yeah, that if you have a very close temperature dew point spread, so if it's like -0, like -1 and -2, then you know that there's a good chance there could be fog forming at that airport. But the point is, it could be kind of a word of caution, like you might have no clouds, you might have really good visibility, and it's like 3 degrees and then 1 degree. But the point is, if it cools even 1 degree further, and suddenly it would be foggy, and it's just kind of it's there to allow you to kind of deduce more information about it.
yeah, so that's actually also how you calculate cloud bases.
Well, that's
Well,
yes
I
and
mean,
no.
like, that's how the FAA wants you to calculate cloud bases.
Yes, because that's the other thing is technically, if I sat here and I did my calculation, if I go 2 degrees of lapse per 1,000 feet, then I should be up 6,000 feet. It should become the dew point. You can see that's inaccurate because it's scattered at 11. So I wouldn't calculate cloud bases that way. You could try to calculate cloud bases essentially just off of the temp dew point thing, but you have to understand that dew point will also drop as you go up in altitude.
Yeah, well, the temperature dew point convergence rate is 2.5.
I don't know, man. I don't.
That's like this, yeah, I don't know, the standard temperature dew point convergence rate is 2.5 degrees Celsius per 1,000 feet. So, I mean, like theoretically, you could like subtract the dew point from the temperature and then divide by 2.5, and then it would give you your cloud bases and AGL, but like.
Well, once again, here that doesn't apply.
Yeah, I know.
It doesn't, it rarely applies. Let's look at well, I guess does anyone have questions about METARs? For the test, we are gonna have to end up reading a METAR. Generally, it'll probably give you a list of METARs and it'll say, hey, this is some, it'll have, and then it'll be like, reference this figure, and then in that it'll say, what are the cloud bases at KHOU, Houston Airport? And you can look in, you can say, okay, the cloud base is whatever it is. You're getting ahead of yourself here.
Oh, what? Did you want something else?
No, here, we'll get there in a second.
A CT.
Scattered. Like, so that just means that,
Yeah, so that means that, and that is actually a good point. There's a bunch of different, I guess there's 4 different cloud designations. There's few, which means there's few clouds. There's scattered, which means there's more than few, and then there's broken, which is more than well, this is actually might not be what you're looking for. I mean, the biggest ways to understand it is it's a certain percentage of the sky. They have it there, and then overcast is complete coverage.
And the number of that is just where that starts.
That's the above ground level height that it starts at.
Is it?
Yes, it's always 3 numbers, add to, add, like, I guess, what am I trying to say? They're giving it in hundreds of feet, so add 2 zeros to it. We don't need this. Go back to Zoom.
what? Yeah.
Any other questions about METARs?
You know, off the top of your head, if the other 2 variations with it,
For what?
or like broken, there's broken.
So broken is going to be BKN, scattered is SCT, few is FEW, few, and then overcast OVC. And overcast is the sky's completely covered. I think broken it's like less than 75% coverage. Or no, it's like less than 80% coverage. I don't know, there's
It's
some,
measured in eighths.
yeah, there's some like numbers that you can assign to each of those. But generally the way to understand it is if it's broken, it's considered to be a real layer. If it's scattered, it's actually not considered to be a layer. It's because technically you can fly around it, but broken, they're too close together for you to fly around it. So if it asked you like, where is the first cloud layer? The first cloud layer is where broken starts. Few and scattered don't count.
Yeah, here's like the official definition if we want it. So few is there's actually one more. There's SKC, which is sky clear. So there's just nothing there. And then few is just like trace amounts of clouds, and then BKN is broken, and then overcast. So it's reported in like terms of eighths. So 1 to 2 eighths is few, and then 3 to 4 eighths is scattered, and then 5 to 7 eighths is broken, and then 8 eighths is overcast. So completely.
Also SKC is not correct. In the METAR, it's CLR would be clear. It would just be CLR in the METAR. I recommend reading some METARs and just looking at some METARs. That will help, because it's not really, I don't know, you just kind of have to look at them, and then you'll have to look online for what certain things mean. Like I said, the part before remarks will be nearly identical every time. The part after remarks will be random. I mean, there's all kinds of things that can be put there, and there's no way you can memorize all of them. On the test, generally, you're not going to be tested on anything there. Yeah, there is a METAR key as well, but all right, let's go ahead and talk about Speci real quick. Well, yeah, we can get over it real quick. Whoa,
TAF or Speci?
no,
Oh, wait. Oh yeah.
you're tripping here.
I am.
Okay, Species are going to be put out by towered airports, right? They're going to be put out by non-auto METARs, and essentially a specie is a METAR that is special. So something special happened. For example, at Metro, they had a peak gust on the day of the Marshall Fire. They had a peak gust of 88 knots. They put it onto the thing is a specie one, and they were like, so they put out a special METAR. Point is, if the conditions are rapidly changing, hourly weather reports might not be good enough, and so they'll put out special reports that help people understand what the conditions are. Questions on that? All right, we'll cover PIREPs and TAPA next time, and then we'll cover all of the rest of this, which is forecast charts and in-flight weather. I know this sucks in terms of the lesson's not really that interesting, but it is what it is.
If you guys want to know how to interpret TAFs or METARs, you can look up this table and called METAR abbreviations from the National Weather Service and read all